short answer, fill in the blank. So as we're going along, if there's something that you want to pull off a slide, just, hey, pause me a minute until you get that typed in. So that part of that quiz listening guide will get filled out today. Some of the questions will be tomorrow, so yeah, don't expect to get all filled out today. And then the final exam is going to be on Tuesday. And I think, I looked and I forget right this minute, I think it's like 30-ish questions. So, the tricky part is, so the reason I have 4 days of fuel systems, and then Case has a big major part of fuel metering and all of that. It had been split up, like, I think like FAA curriculum split it into 2 sections. But then prepware, they put it all into 1 section. They used to separate it, they don't anymore. So when you're studying, it's kind of hard because it's one massive section in prepware. But I will try to remind me if I forget, to post my slides that have the prepware questions, so you can use my slides as a study guide instead of trying to swim through the however many 100 prepware questions in fuel systems, because we won't do any fuel metering in my class. So this one is kind of a prep foundation for Case's class. We'll talk about pumps and strainers and all that kind of stuff, like basic components, and then he'll talk about the cool stuff and the magic that happens. You can see there will be 5 labs. So the first one, that's a Moodle one. None of these are too terribly extensive, thankfully, I don't think. And then number 2, fuel system nomenclature. On the 414, there are components of the fuel system labeled, and you'll take the manual and match up those labels. And then 3, fuel pumps. There's a part 1 where you'll be doing Piper fuel pumps, just bench testing them, and then a part 2 where you're testing the auxiliary fuel pump on the 414. And then 4 is inspecting a 414 system, or actually 5 is. 4 is a Moodle part of that. So, be diligent when we have lab time, because it is only 4 days, fair amount to get done, but I have full confidence you'll be able to do it. And also a lot of it, we'll talk about this when we actually have lab time. There are several labs on the 414, so you can just be kind and loving to one another, sharing space as needed. Okay. Everybody able to get into the fuel systems listening guide? Excellent. We're going to dive into lecture. My hope is that we'll have a little lab time at the end of today, but I'm not going to promise because I know I get long-winded. So, here we go. It's actually not me, it's a curriculum. Let's blame it on the curriculum. So, fuel systems, and for this portion, we are going, you don't have to get it, but a little bit back into the airframe textbook, because that has more on fuel pumps than what the power plant textbook has. We're going to talk about some issues in the power plant textbook, a little bit of AC 4313, and then of course we will go over the regulations applied to fuel systems, trying to make it as painless as possible. So this portion of lecture, I have this one and another one we're going to start into. Hopefully you'll be able to understand, and maybe you already do, differences between carbureted and fuel injected systems, understand causes of fuel systems icing and vapor lock, and regulations. Some of this first part is hopefully for you going to be review from airframe, so not too much brand new stuff in this part. But to help us switch gears from propellers into fuel systems and a refresher from however many months ago airframe fuel systems was, I have 2 short videos to show you to just give a nice, easy refresher. And come on, oh, there we go. Oh,
Many high-wing piston aircraft use a relatively simple gravity-fed fuel system. Low-wing aircraft, and aircraft with fuel-injected engines, will require the addition of a fuel pump. Fuel begins its journey to the engine when you remove the filler cap and fill the tanks. A connection equalizes pressure between the fuel tanks. The vent allows air into the tanks to take the place of burned fuel and lets expanding fuel drip out onto the ramp on a hot day. The fuel selector determines which tank is feeding the engine. Some aircraft have a both position in addition to left and right. The primer pushes raw fuel into the cylinders to help with starting, but you won't find this if the engine is fuel injected. The main role of the fuel strainer is to remove any water or sediment that might be in the fuel. It will collect in a sump beneath the strainer. You'll drain a small amount of fuel from that sump during your pre-flight to remove any accumulated impurities. In the carburetor, fuel is mixed with air in the desired ratio and sent into the cylinders for combustion, but you won't find a carburetor in a fuel-injected engine either.
After learning about how the engine works, we remember that there are two things that are mixed together for combustion: fuel and air. Let's learn some things about the fuel system. The fuel system is designed to bring fuel from the fuel tanks to the engine. In general aviation airplanes, fuel systems can be broken down into two subsystems: gravity-fed systems and fuel pump systems. High-wing airplanes, such as the Cessna 172, are normally designed to be gravity-fed systems. Because the fuel tank is inside the wing, which is located above the engine, gravity can naturally pull the fuel from the tank to the engine. Although, in normal operation, a fuel pump is not required, many high-wing airplanes are still equipped with some sort of fuel pump, either an engine-driven, electrically powered, or both, as a backup for emergency operations. In low-wing airplanes, such as the Piper Arrow, a fuel pump is required to send the fuel from the tanks to the engine. Since the fuel is located below the engine, it is simply impossible for gravity to send the fuel upwards. For this reason, low-wing airplanes are designed with a fuel pump system. Normally, there are two fuel pumps. One of the fuel pumps is engine-driven, and the backup is electrically driven. Some airplanes are equipped with a fuel primer. The fuel primer allows fuel to be injected straight into the cylinder prior to engine start. Fuel priming is especially useful during cold operations. While some airplanes are equipped with a fuel primer, others, like the Cessna 172, are not. However, we'd still like to enjoy the benefits of priming the engine. Therefore, it is possible to prime the engine of the Cessna 172 using the electric fuel pump. Fuel is stored in fuel tanks, which are usually located inside of the wings. These tanks are filled from the top. There is a cap
So it goes more into stuff that's covered in airframe. So, everybody's brain and fuel gear?
on the top that is easy.
So here's the diagrams from the textbook, and like you've already talked in airframe about fuel tanks, how they're vented to each other, how you need a strainer out the outlet, how it goes to your selector valve. Some have left, right, both. Some have off on the valve, some have separate. Some like our MAF 206 doesn't have both, so you're either in right or left and have to calculate, keep track of how much you're using. Goes from there into our strainer. I'm going to talk about the regulation that tells you where your strainer has to be. And then on just a gravity-fed, high-wing, carbureted, have a primer, pulls fuel out, plumbed in parallel. And then our carburetor, Case is going to talk all about that magic. But right here, bam, is our firewall. So we're going to be I'll just briefly talk about a carburetor because we are in fuel systems. So, its job is to take fuel and air, mix them together. And Case is going to talk about this magic. But, what is this? Anyone know, based on shape, what that is in there? Venturi. Very good. So, why is there a Venturi there?
Increased velocity.
Good. Increased velocity, and that draw. Now it's way fancier than this. This is my very simple simplification. Lowers the pressure, so it sucks fuel out of there. Woo! As the air is flowing past, depending how we have our throttle valve open, mixes that air and fuel together. Oh, lucky Venturi was up there. But that's a narrowing point. And if we have a Venturi, which we do in a carburetor, and we are lowering the pressure, increasing velocity, what bad things could happen in that portion of the carburetor? Icing. Very good. And it can, we're going to talk more about specific types of icing in induction systems, but it can build up on your throttle body. It can build up on these little crevices and turns and stuff. So that is the downside of a carbureted system is icing. And here is just a comparison of your nice textbook diagram and what a diagram in a 172N model POH would look like, just so you can kind of orient yourself and say, oh, okay, that's how they're representing a fuel tank. Oh, this one is not vented. That cap is vented. This tank has external vent. We have a selector. There's our strainer, primer, and throttle, and mixture connected to a carburetor, and kind of gotta compare those diagrams. And here's a picture of an actual engine, and our little carburetor is hidden behind our air box. So brings the air in, boom, carburetor. There's fuel connected to the carburetor. That fuel air mixture goes up our induction manifold. I think I only pointed out 3 of them. There's another one back there, obviously. And that fuel air mixture goes up to our cylinders. Boom, power happens. Very quick and simple overview of what is happening in a carbureted system. Any questions on that? Fuel injecting. More common, well, depends you ask. Generally more common, that's not a test. More common comment, but people like fuel injected better, and we'll talk about why. So this is an example of a high wing fuel injected system. So we still have gravity assisting us, taking us to our header or reservoir tanks, going down, still have selector valve. But now, because it's fuel injected and we want to get power pushing that fuel through, we'll have an auxiliary fuel pump that we're going to talk about how that works. It still goes through the strainer, may or may not have a separate primer. And then an engine-driven pump. We're going to talk about these. And then down to our fuel injection control unit that has different names, whether it's Continental or Lycoming. Case is going to talk about those. Down to our distributor manifold, otherwise known as spider, going out to each cylinder. So air is entering our cylinders separately from our fuel. So firewall is going to be, boom, right in there, and we may have some aux pumps on the airframe side of the firewall as well. And also you'll have a fuel flow indicator going to the cockpit to tell you how much fuel flow you have. On here you have actual engine, and I was just curious, you have these teeny tiny little lines that the fuel is flowing through. We're going to talk about that shortly. What problems a fuel injected system could have is different from carburetor system problems. And together, and the fuel and air goes together through the induction manifold to the cylinders. Fuel injected, the servo regulator on Lycoming or fuel air control on Continental. Talk about that in case class a little bit in mine. We're directing air through the induction manifold and fuel through our fuel injection lines, separately getting injected at the intake of the cylinder. Questions on that? Very good. Now, here's a wackadoodle one. We got low wing, but it's carbureted, but like they talked about in that cute little video, we gotta have pumps unless you're gonna fly upside down, which is actually very fun, but gotta take off right side up, it's recommended. We got our carburetor down here, but then we need an auxiliary fuel pump to take it from our low tanks up to our engine, and then we need an engine-driven tank to push that fuel on into our cylinders. So there's all kinds of variations. You can have carbureted, fuel injected, carbureted, high wing or low wing, fuel injected, high wing or low wing, and depending on the manufacturer, they'll have different pumps in different arrangements. So what do you think are advantages of a fuel injected engine as opposed to a carbureted? More fuel efficient when it's a hearse. Higher performance. No carb ice. Inverted flame. Any others? So here's my list, and forget this is in your listening guide. Yes, I think I asked you for 3 advantages of fuel injection over carbureted, so you can just pick 3 of these. But yes, less danger of induction icing. We don't have the carburetor, we don't have the venturi, so we don't have that narrowing and acceleration. So very rare that there's any area in it that could get induction icing. Better acceleration, but more responsive when you push the throttle because all your fuel is being pumped through. It's got pressure. And better fuel distribution because it is evenly being pumped through up to our distributor, our lines going out to our cylinder, so every cylinder's getting the same amount of fuel. And reduced overheating of individual cylinders because they're all getting the same amount of fuel. Better fuel economy because on a carbureted engine, you're generally running your engine so that the cylinder, let me rephrase this. So the cylinder that happens to be getting the leanest mixture is running properly. So all your other cylinders are going to be a little on the rich side. So you're dumping more fuel than is best economy and carbureted. Where fuel injected, they're all getting the same amount of fuel, so you're running pretty even in all the cylinders, not using more fuel than what you need. Any questions on that? Everybody got it in their listening guide? And I will post this so you can go back and fill in your listening guide later if you need to. All right, review from airframe. Avgas, you can see some what on the label, what is the color of the label of Avgas? Red and blue? something they're going to ask you on testing situations. You'll need to know that kerosene has more heat energy per gallon than avgas. And kerosene is also used because it helps lubricate the fuel system components of turbine engines. And jet fuel also has more water, or what is called entrained water. Zach, since you're talking, what's that mean?
He was asking me a question about jet fuel.
Well, what's our problem with jet fuel, with water? Why is it more of a problem than avgas?
It could freeze and also promotes the growth of microorganisms or whatever.
And why is that?
Because that's what they taught me.
So, it retains water a lot more than avgas because the water dissolves in the fuel and is held in suspension, and there's no way to really get that out. So, we do need to use things, I think we have it on the next one, to help prevent microorganisms because they like that watery place and they come and they live in your fuel. Yes.
At the place I worked at, we had like a big sump tank where you dumped all your jet fuel back into, and sometimes it seemed like it would grow kind of like this orange goop in it. Is that the microbial?
It
Or,
could be if it wasn't treated.
yeah.
I wonder. Ew.
Yeah. I was told that it wasn't that, but you know, I don't know what.
They would say that with it.
Yeah.
That's a very good question. Oh, yay. So, these little naughty boys, they can clog filters, corrode tank coatings, obviously degrade the fuel, so now your fuel's not going in the performance it's supposed to. So, we do several things. So, there's Prist is one of the additives that you can use. Also, because jet fuel has icing problems and microbial problems, they often will use solutions that take care of both. So it'll be an anti-icing solution and kill the nasty little bugs. So because dissolved water does form ice crystals, and that can form on filters or in lines, and gas turbines are particularly susceptible to filter ice. So we can either use additives or heaters. We're going to talk about using the oil to heat the fuel. Oil is a fuel heater, or some will use bleeder to heat up the fuel. We're going to talk about that. Different ways to prevent icing. And there is a funny, interesting phrase in, I believe it's your textbook, says, when these ice crystals in the fuel become trapped in the filter, they block fuel flow to the engine, which causes a very serious problem. I would say your engine dying is a serious problem. That's typically sometimes how they phrase things. So there's some ice for you. Now, we're going to talk about vapor lock. So what it is when fuel vaporizes, or kind of boils, in the line, it forms little bubbles, and those little bubbles block the flow of liquid fuel to the engine. When that happens, that's called vapor lock. So causes of vapor lock, things we want to avoid, is when we get low pressure at high altitude, then that lowers the boiling point. You can boil sooner. High fuel temperatures, so getting it so hot that it is kind of giving off bubbles. Excessive fuel turbulence. So if you have fuel sloshing around in the tanks, what do they do to help prevent that? I think I heard it. Baffles in the tank, yep. Mechanical action in the fuel pump can cause turbulence. And if you have really sharp flow completely so that your engine dies. The very best solution, and this is what you will need to know in testing situations, is a boost pump. Because that is smoothly pressurizing that fuel, pushing it through your lines to help scoot any little bubbles out of the way. And you also want to avoid these things. So avoid sharp bends and rises in fuel lines. Try to make them more gradual, any bends. And we do baffling in the tanks. And yeah, boost pump to keep pressure on that fuel. And there is a regulation on this. It was part 23, now 25.961. And it says for fuel system hot weather operation, each fuel system must be free from vapor lock when using fuel at its critical temperature with respect to vapor formation when operating the airplane in all critical operating and environmental conditions for which approval is requested. Mainly, the manufacturer, if they think this could be a problem, they need to have a boost pump. And some engines with very small lines, and these you can see they have a nice gradual curve there. For this example, it looks like a really sharp bend there. So when they design it, try to not have those sharp bends. And anyone that flies that have vapor lock experience, or like, yep. Yep. So very common on a hot day, like this coming weekend, like 90 degrees, somebody flies and shuts down, your engine is hot, now there's not fuel flowing, so vapor can build up. You come along and try to start it, and it's like, nope, I don't got fuel, I got bubbles. So now you gotta try to prime up, but you don't want to flood it, and it's a tricky situation. In which, carefully follow your POH or wise pilots who have gone before you. Funny story on that, I think, yeah, I'll throw the story in here. So when I was student pilot, I knew nothing of maintenance, like nothing. And my flight instructor, he had just got his CFI, I was his first student, so it was interesting. But after I had done my first solo, and then I was renting the airplane, but somebody had just flown it, and I hopped in and I tried to start it. I don't know if I even knew. I'm sure he told me about vapor lock, but it's probably right over my head. And so I went to start it, and nothing happened. Tried to start it again, nothing happened. Started. And the airplane was sitting right across the ramp from the maintenance shop. And so I started to see the maintenance guys go, they start, what? Student, oh no. But then one kind soul, he came over, he's like, hey, what's going on there? I was like, I can't start my airplane. So he hopped in and told me about vapor lock, and he started it up for me. And so I appreciated it. Forget his name. Anyway. So if you're ever in that situation where you're working at a FBO or that has rental aircraft, and you see a student struggling, you can pass the kindness along. Hey, your instructor told you about vapor lock. Let me explain this. So, what are chief causes of turbulence? Sloshing. Pump action. Tight bends. Sharp rises. And boom. Nailed them all. And this is something you need to know. To reduce the possibility of vapor lock, fuel lines are kept away from sources of heat. They try to. I mean, you got to be close to the engine because you're going into the cylinder. But this is what they say. Also, sharp bends and steep rises are avoided. Okay, we'll go a little bit more, and then I'll give you a break. So here are our regulations. Rather than making you dig out your books or go online, I put it all right here, bringing out the important things that you need to know. So I have the references from 23 on here because cleanest. This has become old part 23, and hopefully Kirk talked to you about that, and they sprinkle it into other sections, or else it goes into manufacturer stuff. But anyway, the information is what you need to know, not necessarily where you find it. So fuel flow for gravity systems, because we might not have a pump, it must be 150% of takeoff consumption. So if they're not reaching that, then they got to put a pump in the system. So gravity must be at least 150% of takeoff. And fuel pumps, so here's what it says. For reciprocating engine installations having fuel pumps to supply fuel to the engine, at least one pump for each engine must be directly driven by the engine. So that makes sense. If you have an engine-driven pump, you must have at least one engine-driven pump. So I'm not trying to trip you up. They're trying to say, if you have two engines, you need one pump. Or if you have one engine, you need two pumps. Like, they try to trip you up, but one pump per engine driven by that engine. Then, fuel shut-off valve location. A lot of these are very common sense. You must be able to shut off your fuel, and that shut-off valve must not be on the engine side of the firewall. Now, there are remote shut-off valves, because you'll shut this off, and later on I have a diagram of where that actually goes in the mechanism that shuts off the fuel. But that must be not on the engine side of the firewall, because if your engine's on fire and you got to turn off that fuel, you don't want your fuel valve to burn up, and now you're just dumping fuel into that fire. So, not on the engine side. And then fuel strainer location. It must be between the fuel tank outlet and the inlet of the fuel metering device. That makes sense, because we want to protect our fuel metering device, because it has fine passageways that stuff can get clogged in, so we need a strainer before our fuel gets there. And then we need a positive means of shutting off fuel to all engines. So you can't have shut off just to one engine. Every engine must have positive means of shutting off the fuel, which makes sense. Make sure you know where your fuel shut off valves are. So in this is like Juliet Serra 172N model. The shut off valve is the bottom portion of the fuel selector valve. On the fuel injected 172s, our selector valve is just right, both left, and then we have our fuel shut-off knob just above that you would pull. And here is that fuel shut-off knob, but now it's going the whole way close to the firewall. The firewall is here, and it comes back. Here is they blow that up, and just to a mechanism that pulls the valve, shuts off the fuel. Make sure when you're getting in an aircraft, you know and positively identify how to shut off the fuel in your aircraft. Very important. And the POE will tell you that. So, where is the engine fuel shut-off valve usually located? I take a class boat is after the firewall, adjacent to the fuel pump, or downstream of the engine-driven fuel pump. You can give me right hand for A, left hand for B, both hands for C. Very good. After the firewall. And off. We're almost making it through, but go ahead. Take a break. Come back at 40.
Second?
Which one is it? include which of the following? Is it an engine-driven fuel pump and at least one auxiliary pump per engine, or positive means of shutting off the fuel to all engines, or a reserve supply of fuel available to the engine only after selection by the flight crew sufficient to operate the engines at least 30 minutes at need open hours? So we've got A, he's going for, does every certificated aircraft always need a fuel pump? And I'm getting this. So, if we, I actually got some,
It has to have a fuel pump, but it doesn't necessarily have to have an auxiliary pump, right?
Does not have a fuel pump either.
right.
And a fuel injector.
Does and you can look at Juliet Sierra. Juliet Sierra is 172 N model, carbureted, high wing, only relies on gravity, no fuel pump. So they're not super common anymore, but high wing carbureted does not require a fuel pump, as long as it's meeting the next question's requirement. We'll talk about that. So, to the whole class, what is the correct answer? It is. So, every single certificated aircraft must have a positive means of shutting off the fuel to all engines. Any questions on that? Alright, so here is for Austin. The Federal Aviation Regulations require the fuel flow rate for gravity systems, main and reserve, to be, which one of those, 125 or 150%? Well, Austin, you're looking a little different today.
I would respond as
He was like, I saw him, and then you're like, bang. Okay.
sorry,
Well, Zach took it, Zach stole it.
sorry, I didn't mean to.
Apologize to Austin, stole his question. Yes, it is 150%. Austin. 150%. So, back to the 172 N model, high wing, carbureted, doesn't need a pump. If it couldn't meet this, then it would need a pump. So if it's gravity fed, meets 150% without gravity feed, we don't need a pump. Is that any questions on that? Alright, Austin, I'll just give you this one. You don't get off the hook. A fuel strainer or filter must be located between what? Boost pump and tank outlet, or tank outlet and fuel metering device, or boost pump and engine-driven fuel pump. Very good. Tank outlet and fuel metering device, because you want to protect fuel metering device. And layout. Fuel lines are kept away from sources of heat, and sharp bends and steep rises are avoided to reduce the possibility of what? Vapor loss. So this is one they really like. They'll ask you different ways, different times, different ways. And Anthony, kerosene is used as turbine engine fuel because it has very high Did you have an answer? Very high volatility, which aids in ignition and lubrication, or more heat energy per gallon and lubricates fuel system components, or it does not contain any water. And which one? Excellent. More heat energy per gallon. And ooh, I'll do a whole class on this one. We didn't talk about this. This is a review from Airframe, and I won't tell you which class we also talked about it in. That'll give it away. Fuel cross feed systems are used in aircraft too. I'll read through and then I'll let you vote right 2019. So we are going to talk about this whole presentation has primer pumps, engine-driven pumps, auxiliary boost pumps, ejector pumps, strainers, filters, fuel heaters. I believe we're going to get somewhere in here. So we'll see. So by the end of this lecture, which end will be tomorrow, you should understand components and operation of fuel pumps, strainers, filters, and fuel heaters. First thing I want to bring to your attention is errors in your textbook. So if you don't have your textbook with you, you can just jot this down, or I will also be posting this tomorrow. So in your textbook, and I just took a picture of the page 2-41 in your new textbook, it has categories of fuel pumps and a description that is completely wrong. Like, it's very messed up. Yeah. So this textbook came out last year. So I was reading, which I was really glad I did. And I was like, what in the world? So I took it to Ryan to make sure I was thinking correctly that it was wrong. He's like, yeah, this doesn't even make any sense. So, and then he called his dad and talked to Dwayne, so he got all these confirmation that it was completely wrong. The old textbook, my good old faithful that I had when I was a student, is correct. So it has correct categories of pumps. Ryan emailed the FAA, and they got back and they said, oh yes, it is confusing and incorrect, and they are going to change it in the next revision. But for now, it's wrong. So, page 241, engine fuel system components, main fuel pumps. That first section and paragraph, we just put an X through. And for you guys, like, you are very welcome to come and look at my actual copy, or you can use this slide. Also, Jefferson is a really good text as well, if you want to use Jefferson to review how pumps work.
The
Yeah.
old one's correct?
Yes.
I think the digital version has them.
Really? I didn't
Looks
check
like it.
that. Well, that is very encouraging, because they may have updated it digitally. Obviously, they couldn't on the print ones.
And it's just at a glance, it's looking all the same pretty much.
I think our digital is the old one.
Oh, that makes sense.
It's always one big
Okay.
page number.
So, thank you. So make sure you're using the digital that matches this if you want to read through that. So, the printed that has that, you can just X that out. Just read that. Okay. So, fuel pumps. Where all might we have fuel pumps in our fuel system? So, on engine-driven, what'd you say? In the tank, because we might want to transfer from one tank to another, or a low wing, transfer from our tank up to our engine. So they can be up here between tanks. We can have an auxiliary taken from our tank to our main fuel pump. We can have primer pumps, engine-driven pump, auxiliary fuel pump. So we're going to talk all about those. We'll start off talking about our little primer pump. And this will be in parallel, pulling off our main line of the fuel strainer. So our fuel's all nice and strained. And then it's going to be going to our cylinders. So draws fuel off the branch from the fuel strainer. It is parallel to the main fuel line. And these are very simple pumps. All it does, so this one, we took the inside out. So you just draw back on that, it sucks fuel in like a syringe through a one-way check valve, and then when you push it in, it squishes the fuel out a second one-way check valve and forces that fuel into a cylinder, or maybe you might have primarily 2 cylinders. Very little maintenance. If they break, replace them. It is very important when the engine is running. Otherwise, it's going to be just sucking extra fuel, and you could be running way too rich in your engine, possibly even kill it if you're overfueling it. So make sure your primers are locked when you're not wanting to prime your engine. And this shows, here comes our main fuel line, here's our strainer, and the primer's up here, sucks the fuel up, swoop, and then pushes it out to our, whichever cylinder the engine manufacturer says receives that prime. And I have a video of a guy taking apart primer. Maybe.
Don't forget to like and subscribe and check out the rest. Hey everybody, welcome back to the Ayers Aviation Hangar. Today we're going to talk about fuel primers, but before we get started, don't forget to like and subscribe to the channel. Help me, help everyone else out. It'll help push all my content further out, reach more people in the aviation community, and if everyone becomes more knowledgeable, make everybody safer, keep the skies safer and stuff. So be sure to like and subscribe. So today we're going to be talking about fuel primers. Just like all the other systems I talk about, you're only going to see about this much hanging out the instrument panel. The rest of the whole system is behind the instrument panel and you don't see it. It's a very simple thing, but at the same time it can be pretty dangerous if you're not really paying attention. Okay. So what does the fuel primer do? It acts just like a syringe. So I got a little baby syringe here. Okay. When you pull the fuel, or you pull the primer back, it fills that cavity full of fuel. When you push that thing forward, it pushes fuel into the engine, and that either goes directly into the cylinders or into the intake manifold. So when you start the engine up, there's more fuel initially to help fire the engine and get it going. So when you pull this thing back, and I'll take it apart real quick so you guys can see the inside. All it is a couple O-rings, and so this is your plunger, and it slips inside here. And I just bought some silicone lubricant stuff. It's in a little bitty, just a little bitty pouch off of Aircraft Spruce for like $4, and it really works well. So when you pull this plunger back, it draws fuel in to the cavity, and when you push it forward, it pushes that fuel into your intake manifold or your cylinders, however your aircraft is designed. Very simple concept. It can be really dangerous, so I want to show you guys something that a lot of people overlook, and every pilot's done it. We try not to do it because it can be dangerous. It can kill an engine. Is this little barb right there. Okay, everybody see it? Kind of hard to see. That little barb needs to fit in a little bitty tiny hole in the primer. Everybody see that? So when you push this thing in, it needs to go inside here, and you want to rotate it about half a turn, so that way the primer can't come back out a little bit. If it does come out, then when the engine's running, it can continually suck fuel through this primer and into the engine, and it puts way too much fuel in the engine. It can cause it to run really rough or even kill the engine. So you definitely don't want to have that happen. Like I said, it can turn something just that simple can be really dangerous or even fatal. You definitely don't want that to happen to you. So just a quick video about fuel primers. Hope you guys liked it. Don't forget to like and subscribe and check out the rest of my videos. Appreciate it.
Oh, thank you, sir.
And hope you have a more
Any questions on that? So, for priming, so horizontally opposed, usually one, maybe two cylinders, manufacturer tell you which ones. But they want you to know that on radial engines, priming is limited to the top and horizontal cylinders to avoid hydraulic lock. And if you're putting fuel in down here and then hydraulic ones, and they'll be like 5 and 6 or 7 and 4, and you're like, it'll be 1, 2, 3, 8, and 9. So that's something they will ask you. And hand pump primers are common on gravity feed fuel systems. Well, very, very common. And if it is an electric priming system, and they'll ask you that on an electric priming system, how does this work? You get fuel pressure by the boost pump, and that's an electric pump. We're going to talk about turn on. You get your prime from that. Now we're going to dive into pumps. So there's different ways to classify them. One way they're classified is this. We have constant, or otherwise known as positive displacement pumps. And these pumps, typically, these are gear pumps or vane pumps. And as they rotate, they are moving a constant specific volume of fluid with each rotation. So that amount is constant every time, because they're scooping up that same amount every time it's turning around. Then we have variable displacement. So these are general, well, actually I won't say that. So pulsating piston and centrifugal, which we're going to talk about that. And depending on the demand and the load, the output will change. So it is variable. Changes depending on the demand, what it's asking for, or what the pilot is telling it, how fast it's going to be turning. Another way to group them, which this is how I did it for this lecture, is engine-driven pumps and auxiliary or boost pumps. So engine-driven pumps must deliver a continuous supply of fuel at the proper pressure at all times during engine operation, and they are geared to the engine. The engine is driving these pumps. And then we have auxiliary or boost pumps, electrically powered with a little motor, and they provide fuel under positive pressure to the engine-driven pump. So the auxiliary or the boost is there for the engine-driven pump. So that's the engine-driven pump's buddy giving him positive pressure. That is the primary purpose of an auxiliary pump. They also transfer fuel from one tank to another, but that's not considered their primary purpose. And primary purpose of engine-driven is continuous supply of fuel at the proper pressure at all times during engine operation. If those were some, maybe not, on your listening guide. So, now we're moving into engine-driven pumps, so geared to the engine. Vane type pumps are most common on recips, according to your textbook, according to the people that will be testing you. So, vane type pump, most common. Tuck that away into your knowledge. And they will be positive or a constant displacement. You'll see both of these, depending what textbook you look at. Positive or constant means the same thing. It means a constant volume of fluid with each rotation. If we are always moving fluid whenever the engine is running, what does our pump need to have? A relief valve. So engine-driven pump requires a pressure relief valve, and elongated a little bit. So as the spacer is pushing these veins against the rotor, this is turning, drawing fuel in, scoops it up. We have big space up here, nice amount of fuel. And now this space squeezes down, so the easiest exit is out this outlet. So fuel's getting scooped up around outlet, veins come around, scoop up more, and it continues. And I have a video on this. I'm going to only show the first like 3.5 minutes. It's like a 20-minute video, so if you're interested in looking at it, because he shows some really cool stuff, you're welcome to later.
Hello, in this video we are going to discuss the Titan, or Romac, constant displacement engine-driven fuel pump. Alright, so what makes this pump work? Let's take a look at it. First thing I want to talk about is just the very basic pump, which if we take it down to its basic component, it's just a pump with an inlet and an outlet. And so right here, as it's labeled, we have an inlet, and fuel would enter this area right here. And here we have a rotor with some vanes that slide in and out. So these vanes right here are either steel or it can be carbon. And what happens is this rotor will rotate around. The engine will drive this rotor, allowing these vanes to slide around inside of the rotor, creating both small areas and large areas, or voids, if you will. So as this turns around, you will see that fuel comes up into here, and it is pulled by these vanes rotating around. And so it'll be pulled up into this chamber right here. And then as this vane rotates around, we'll have another chamber here. But as it starts to come around this way, what happens is it starts to get smaller and fuel has nowhere to go. And so the fuel is then forced out and through here down to the outlet. So let's take a look at an actual pump here that I've taken apart, and you can see that this right here is the rotor that fits down inside of there, and here are the vanes that would slide around, and here's that little pin that's right in the middle. So we would look at it like that, and that allows the vanes to move around inside of this eccentric hole. And so that is going to, I'll put it in correctly, we'll set that in just like that. And now you can see how, if this is the inlet coming in this way, how as it goes around, the vane right there would come around, and because there's no space right here, it's going to force fuel to go that way out the outlet. Let me put the vanes in here. We'll take another look at it. All right, so I've inserted the vanes in there, and now we can take a look at it. So we will rotate it around, and we can see how the vanes will slide and move as we rotate this. So the way I'm rotating it right now, this would be the inlet side right here. So fuel would come in this way, be drawn through here, and as it enters this chamber over here, you can see how the space gets very small. Fuel has nowhere else to go, so it's going to be forced out the outlet right here. Now if I turned it the other way, we would just have the inverse of that. This would be the inlet side, and the same thing would happen. Have a space here, but the space gets very tight right here, forcing fuel out that way. So that is really the very basics of the pump and what it's doing and how it pumps. So while we're talking about rotation, it's important to note that when we talk about the rotation, it's not viewed from this end, but fuel pumps or any engine-driven accessory, whether it be a fuel pump, magneto, or whatever you have attached to the engine. We'll look at this pump right here. The direction of rotation is when viewed from the drive end. So this is the drive end. And so if we rotate it this way, it would be a clockwise rotation. And if we turn it this way, it would be a counterclockwise rotation. So all right, that's the basic pump.
So I got this little guy. I don't want him to come off. This is a little engine-driven thing. Hold. Yeah. Uh-oh. Stay there, little hear what direction it's going, and just take a little look at the little pump. So what I'm passing around is very similar. This is a newer model of it, but engine driven. And then inside are the vanes that the engine is geared to, turning around. And we talked about, oh, actually this one is Hartzell Engine Tech 200 Foxtrot series. Lycoming used this in their fuel injection system. And there's a whole bunch of ABs that came out on this for pump failure, a certain year, certain number of hours in service. So just when you're working on stuff, make sure you're looking at your AB. But we're going to talk now about our pressure relief valve. So it's pretty cool how this works. If we have fuel normally coming in, flowing around, and going out our outlet, but what if our engine said, I don't need all that fuel, and we start to build up pressure. Pressure begins to build up, and woohoo, it goes through our little relief valve. So we have a pressure adjustment screw and a spring. So what happens is, as pressure builds up, it pushes up on this bypass valve plate that pushes up, overcomes the pressure on the spring, allows fuel to flow back. So that is an adjustment that we can make depending what the requirements of our engine are to allow this to be less pressure so fuel flows back sooner. Or if we want more fuel in our engine, then we put more pressure so it takes more pressure to push that plate up. And things you need to know. It is, the pressure relief valve is required on positive displacement pumps because they are always pumping the same amount every time. And it directs excess fuel to the inlet side of the pump. So like in the diagram, just right back to the inlet, recirculates. So it directs fuel that's not needed to the inlet side of the pump. And you adjust it by the pressure adjusting screw, which changes the tension on that relief valve spring. Yeah, of course, they took that concept where an actual human being adjusts the tension on the relief valve spring by adjusting the screw, took that concept and they're like, we think we can make this automatic. And of course they did. So they call it a compensated vane type pump, which means its relief valve compensates for whatever condition it's in. It's also called a balance type relief valve. So compensated or balanced type, you'll hear these names. And this is used if a vane pump is the primary engine-driven fuel pump. There's other types of pumps. And the relief valve setting varies automatically. So we have a vent connection that goes to our fuel metering device inlet air pressure. So that is sensing whatever air pressure is at our fuel metering device. So that may be just whatever's in the manifold. Or on a turbocharged system, it's going to sense the pressure coming off the turbocharger. Show that in the next diagram. And we have a diaphragm that gives us our little vent chamber. So what happens is, instead of us adjusting this to got more pressure pushing on this diaphragm, which is pushing on this down here, which is putting more tension on this plate. So if we have more air, we want more fuel to match that more air. So we want more pressure in here before we relieve it back. Now, if we get up to altitude and a lower air pressure, well, we want to reduce our fuel a little bit so we're not running too rich. So then this is going to say, oh, I'm at high altitude, I don't have very much air pressure. Got to relieve on the diaphragm, which brings the spring back, which lets this lift up at a less pressure so fuel can relieve back at a lower pressure. So, compensated or balanced relief valve provides the correct amount of fuel based on changes due to altitude or turbocharger outlet pressure. And it has the vent chamber, the diaphragm, and the relief mechanism. Any questions on that? Yeah.
I just don't understand, isn't it really the job of the fuel metering device?
It is.
To, like, control how much fuel gets delivered?
Correct.
So why can't we just have maximum over time?
So this is kind of a backup to that, and if you have a vane type pump, let's say on a low wing, carbureted, it can compensate for that. So, yes, your fuel metering is going to do way fancier stuff than this, but this is sort of a backup to that, or if it's not, if it's a carbureted system, low wing, or we still have an engine. That's a very good question. So, this can be vented just to atmosphere for altitude changes, or it can be vented to what is called upper deck pressure. Here's a quick rundown of a turbocharger. We're going to have that class separately, but the turbocharger is driven, the turbine driven by exhaust gases coming off our engine. The turbine drives a compressor, which is compressing our intake air coming into our cylinders. So between our compressed turbocharged intake air and our throttle body is called upper deck pressure, so that's what that little sensor is sensing on our relief valve. So this is the other name, so either compensated or balanced type. So generally it'll be called a compensated vane pump. Compensated vane pump has a balanced type relief valve. Designed to use a diaphragm to compensate fuel pressure for atmospheric pressure, including altitude variations, and the chamber is vented to the atmosphere in normally aspirated engines, but the upper deck pressure in turbocharged engines. Questions on that? Then, what else do you think we should have in our little engine-driven pump besides a relief valve? What did you say?
Set a filter, but
You definitely need a filter for it. It won't be in it. Very good thought, yes, a shear shaft. If it breaks, what else if it just quits working? Backup. How about a bypass? Nailed it. So, on the, so here's our relief. So the relief is to allow fuel to flow backwards if we're having too much pressure. But if the pump croaks and this dies, we still want a way for fuel to get through. So there's a bypass valve plate. Hang with me.
So if the pump breaks,
Yeah.
then the fuel pump bypass valve allows fuel to go, but if the pump is broken, how to get the fuel?
You just wait and see. Well, an engine-driven pump, what do we need in the system?
Auxiliary.
Yes. So this is why, and again, this is exactly what you experienced in the story you shared the other day, which is a really good story.
Yeah, I did experience that.
So,
Mine was just
can you
like-
share it in 3 minutes?
Yeah, I took off actually out of here on a flight, and then when you get to pattern altitude, you shut off your auxiliary because you don't need it. And I shut it off, and usually people mindlessly look away, but I always check it and realizing my fuel pressure plummeted to 0. So when I turned it on, well, back on, because my engine quit, and I made a decision to fly all the way home at 5,500 feet. And I was only like 10 miles away.
But he was being a very good and competent pilot, saw his fuel pressure drop, was like, oh no, my engine-driven pump has bit the dust, died, not working, but back on the auxiliary pump. So auxiliary pump was able to push the fuel, even though it couldn't get through here, vanes weren't turning, or probably another type of pump. Anyway, was able to push it through the bypass, boink, push down that little weak spring with the plate, and fuel can still flow to the engine. So a bypass, when it opens, exact scenario, it opens and remains open if boost pump pressure is greater than fuel pump pressure. So normally it's given at the same pressure and what it needs, but if our boost pump pressure exceeds engine-driven fuel pump pressure, it's going to say, uh-oh, engine-driven fuel pump has died, we're opening up that bypass. And it allows the fuel to flow around the engine-driven pump for starting, because when your engine isn't started yet, obviously it's not turning your engine-driven pump, so it'll send fuel around it for starting, and then also emergency operation if your engine-driven pump dies, and it prevents an inoperative pump from blocking fuel flow. Any questions on that? All right, take a break. We'll talk about some more pumps. We come back at 35. That's not in your textbook at all. They don't really ask you questions about them. But they are very, very common. So I don't know why it's not in your textbook. So this isn't textbook stuff. This is real world maintenance stuff. So diaphragm pumps, also known as AC pumps. Lycoming likes them. Piper likes them, which might tell you a little something about them. And they operate by lever action. We're going to look at how this actually is installed on the engine. But this is a pump, lever, however you want to say it. And it pumps, and it pumps a little diaphragm up and down, which draws fuel in, pushes fuel out. Draws fuel in, pushes fuel out. That's how it works. Very basically. We have a fuel inlet and outlet, and something very important to know about these pumps, there is going to be a vent on them that is on the side of the diaphragm that should not have fuel. So when you inspect these pumps, just a visual external inspection, you should know what part is that little vent, and if you see fuel dripping out of that vent, that means the diaphragm has died, or it has a hole in it, and now it's not going to do its job because it has a leak, and it's not going to be able to draw fuel in and to push fuel out anymore, and you're not going to get the proper supply of fuel to your engine. It also has check valves that we're going to talk about, and those can get all gummed up with debris. So these are not the best, not the most reliable, but Piper likes them. I'll show a video of these, and this is also a longer one. I'm just showing the first about 3 minutes. You're welcome to look at more of it later. Oh no, it is 3 minutes. Okay.
This is a mechanical fuel pump taken from a Piper Warrior aircraft, but it's typical of a mechanical fuel pump in most light aircraft. If the aircraft was a low wing design, then it would be supported with an electric fuel pump, which would be used at appropriate times of flight. It fits into the engine block like that, and this lift pump rocker arm is operated by an off-center cam, a lobe which presses down on it and it lifts a diaphragm in here. Let's take it apart and have a look inside. Now, to demonstrate how this works, I'm going to have to place it into a vise to show you how, by rocking this arm, the diaphragm moves up and down. Now, the cam lobe spins round and round here, and it pushes down on this arm. And what it does is, you can see how the diaphragm moves up and down. And that diaphragm moving up and down is going to suck fuel through a one-way check valve. As the diaphragm moves up, fuel is sucked via a filter through this aperture here, through the one-way check valve. As the diaphragm moves down, fuel cannot go this way, it can only go through this port here, which also has a one-way check valve, the opposite direction to this one, and the fuel exits here. And it's as simple as that. This whole pump is usually fitted just in front of the firewall, and you can see on the diagram to the left there where it's fitted on that particular engine that I'm showing you. And just finishing off, we'll look at this schematic for the DA40, and you can see the position of the mechanical fuel pump. and that's supported with an electric fuel pump which is further downstream.
And I bought that portion that he was showing with the little check valves. So I'll pass that around, and I'll also pass this little cutaway. You can see kind of the diaphragm, spring, lever. Seen better days.
So what's moving the lever down to?
We will look at that. It is a special lobe off of the camshaft with a plunger. Whoop, there we go. So, some things to be aware of as you're doing maintenance on aircraft. In the manual, it may be called AC pump. And things that go wrong, debris in those check valves. So Gavin has the check valves right now, but debris can get in there. It's simple, but simple can go wrong fairly easy. And then looking at the drain, because if there's fuel coming out of there, that means you have a leak in your diaphragm, so that diaphragm won't be able to draw the fuel in. And Piper, especially Piper Lycoming combinations, like to use this diaphragm pump. And here is, this is an example from Lycoming 03.20 IPC. So you can see we got our pump here, and I'll go into our engine. And then if we go to our, this is the direct drive overhaul manual, table of the limits and gear train from Lycoming. So this is showing, it says our AC fuel pump is going to go down here onto this plunger. This plunger is going to this eccentric drive, and this is actually the crankshaft idler gear, so depending on the engine, there'll be a little different arrangement. But this, here's our AC pump, and here's that lever, and that goes to this plunger, which is going to that eccentric portion of the idler gear. So, and I'm sure Ryan's going to go over this with you, but it is very, very important when you install this on your engine that you are making sure this plunger is up as you're putting in your little lever of your pump. Otherwise, you could be doing, so that plunger has dropped down, and you shove your pump in there, and it goes clonk, and then your engine starts to operate, stuff's destroyed. Pump's destroyed, plunger's destroyed. Plunger then destroys, because it's not going in its right place, your eccentric gear, which is destroying the rest of your gears in your engine. So that's really, really bad if you're not paying attention and you're just shoving this in against that plunger. Make sure it is up, pushing down on your lever. And then it will do a happy little thing off of your eccentric portion of your gear. And then here is the direct drive overhaul manual. It will give you torques for your Allen head screws. Also the vent fitting gives you a torque for that. So make sure you're paying attention to all that stuff when you're installing one of these pumps. And be very aware. So this is Continental has a service bulletin for their camshaft part number and the fuel pump part number. They must be the correct fuel pump for specific camshaft on Continental, because you can have all different styles or types, purposes of diaphragm pumps. So this one, this is a Continental service bulletin, but I just happened to grab Lycoming fuel pumps. So make sure you're getting one for Lycoming if you have Lycoming, Continental if you have Continental. And then, like this one, is for a smaller engine, 4 to 6 psi. This one is 25 to 30 psi. So don't put the wrong pump on your engine. And this is then even a different model number. So extremely important to make sure you got the right one. There is a service bulletin from Tempest on the pump lever wear. So, and I have it printed out where you can look it up online if you're ever interested. But they became, and this is one maker of these pumps, recently become aware of atypically worn fuel pump drivetrain components on some engine applications. It appears this condition can result in damage to a fuel pump's lever, create possible misalignment between the push rod and pump's lever, and result in pump becoming inoperative if allowed to progress to a point that the push rod migrated completely off the lever. So, some of these got so worn that the push rod that's doing the job of making it go up and down migrates and totally falls off of the lever. Now pump can't work. So that's, yeah, just one example of one type of diaphragm pump that has a service bulletin. And then Lycoming. So we can have Lycoming, Continental, or Piper, or Tempest, the manufacturer of the pumps. All these are putting out service bulletins. Mandatory service bulletin, and this is on specific Lycoming models. And it says may not have been manufactured, so it was not something that went wrong afterwards. They weren't manufactured right to begin with. In conformance with acceptable standards. And then it gives you what to look for to know if your pump needs to be replaced or not. Why are these things important? Well, back in '96, a pilot was flying at night over Lake Michigan. And this is never a good start. In IFR conditions, when he informed Milwaukee Approach that the engine had quit. He was 20 miles northeast of Milwaukee. He was able to glide about 12 miles before impacting the water. And this was in January. The body of the pilot and airplane were recovered about 2 months after the accident. Examination of the engine-driven fuel pump revealed that a 3/4 inch rubber washer was restricting the fuel flow through the outflow valve of the pump. AD 9311-11 states that the remanufactured fuel pump was to be replaced before the next flight in order to prevent disruption of fuel flow to the engine, which can result in loss of engine power. The AD had not been applied. So, very preventable accident. And maybe the pilot may not have had any idea, but whoever was maintainer of the aircraft didn't comply and somebody died. This is the AD that it was talking about, and this AD refers to a service bulletin that shows you how to comply with it. And yeah, it just directs you. These are really nice service bulletins because they give you specifics to look for, where to look at the model number, serial number, and then what numbers you need to throw out and replace. All right, time for your mechanical eyeballs and brains. Do you see anything wrong with this situation? With the pump specifically. I heard somebody. Yes, it is missing safety wire. I think. Okay, I thought I heard it over on this side, but yeah, there is no safety wire on that. So be looking for stuff like that, simple stuff. This was a couple years ago. purpose of the diaphragm in most vane type fuel pumps is to maintain fuel pressure below atmospheric pressure, equalize fuel pressure at all speeds, or compensate fuel pressure to altitude changes.
Charlie? One of those three.
So, I'll throw it out to the class.
Kind of dozed out on that one, sorry.
When would a vane, what type of vane type pump has a diaphragm? Compensated. And what makes it a compensated vane type pump? It has a compensated or balanced type relief valve. So then, it is, Charlie. It compensates fuel pressure to altitude changes. So if you kind of link that, diaphragm, vane pump means compensated balance. And Josiah, fuel pump relief valves designed to compensate for atmospheric pressure variations are known as which one of those? Compensated flow valve. I'm going to give you a second opportunity. Pressure relief valves or balanced type relief valves. That's tricky. Yes. So it is a balanced type relief valve or compensated type. They threw flow in there. It's not the valve itself. Fuel isn't flowing through the valve itself, so it's not compensated flow. So that's called compensated pump or balanced type relief valve. And it's one of those things before you go for your written and oral, just kind of memorize the words.
So a balanced type is the same as a compensated type.
Correct.
Why would they do that?
Because it is. I don't know. Okay. going to be our supplying pressure to our engine-driven pump. They can also be between tanks, but that's not for engine class our primary concern. And you can see them shown in a diagram in different ways. So, number one, primary purpose that you need to know for a boost or auxiliary pump is, its purpose is to provide fuel under positive pressure to the engine-driven pump and during starting. And it's a backup to the engine-driven pump during takeoff and at high altitude to guard against vapor lock. And then also used to transfer fuel from one tank to another, not the primary purpose, but it helps with that. And so what does the textbook want you to know is the primary type of engine-driven pump? Vane. Vane type is the most common engine-driven pump. We'll see a fair amount of diaphragm on ours, but the most common engine-driven is vane. Now, the most common boost or auxiliary is centrifugal. So centrifugal, most common for auxiliary. Don't get them mixed up. We, in small general aviation aircraft, will see vane type auxiliary pumps, but most common overall is centrifugal. So this should be a review from airframe, but a centrifugal pump is going to have a motor turning the pump, and they can be mounted submerged within a fuel tank if they're for transferring fuel from one tank to another, or mounted outside of the fuel tank. And if, this is something you'll need to know, they're mounted outside of the fuel tank, it has to have a pump removal valve handle. So when you take that pump off of the fuel tank, you don't just lose fuel like crazy out of that hole where it was. It'll have a valve that you need to close that allows you to remove that pump. And then they will have inlet screens to protect that pump from any nasties coming in with the fuel. The internal workings, and again this should be a review, there is an impeller that is actually pumping that fuel through, and it comes up, there's a check valve that prevents backflow, whoopsie daisy, and some will have a bypass valve, but the speed of this is going to be selected by the pilot. Some just have one speed, but many will have more than one speed. And I've got some centrifugal pumps here. Okay, so I can pass them together. But on this one, I pulled this little screen back, and you can see the actual impeller inside. It goes around. Oh, look at that. And what you need to know for engine fuel systems class on centrifugal auxiliary pumps is that they separate air and vapor from the fuel. So by the action of our impeller and sending the fuel up here, that does separate air and vapor, so you get fuel headed to your engine-driven pump. Yes.
Is it the same one that like the Cherokee uses, the one that's out on the table?
No. We're going to talk about this next. Yeah. These are more in larger aircraft. And because it'll change its speed based on demand or pilot selection. And if it dies, it does have to bypass. The fuel can be drawn through an inoperative impeller. So, dies and still take fuel through that. Now, this is the pumps the Piper likes, the pulsating electric pump. So what happens is we have on here a steel plunger in the center of our pump, and we're talking about these styles of pumps now on Cherokee Pipers. So what happens in the internal workings, we've got steel plunger. As that goes down, and that is energized by this solenoid coil, so that pulls this plunger down. Any fuel that's down here in chamber C, according to this diagram, gets squishes up through the plunger, up through a check valve, up into chamber B, which is the outlet, and squishes it out to the outlet. When this plunger is down here, it pulls apart from the magnet these electrical contacts, which turns our coil off. So coil's not pulling it down anymore. Then the spring overcomes it, pushes the plunger back up, and that draws fuel into this chamber. Oh, there's our magnet. Calibrated spring. So this happens very fast. So energized coil, plunger down, squishes fuel out and up. As soon as it's down, contacts separate. So then plunger's going back up, drawing fuel in the bottom. That closes the contact, sends it back down. The thing that's resisting that up and down movement is the pressure of the fuel up here. So as we build up pressure, because our engine-driven fuel pump is getting enough pressure, that starts to back up and puts pressure on our plunger, which eventually equals or comes close to equaling this spring pressure. So if you've ever flown a Piper and you turn on your auxiliary pump, you'll hear a noise. I woke some people up. And that's this poor little plunger going up and down really, really, really fast because it's got no resistance up here. So as soon as it hits bottom, that spring's pushing it back. As soon as it comes here, contact closed, pushing it down. It's going super fast. But as it's doing that, it's drawing fuel in, sending fuel up, sending fuel out. Now we're building up pressure. As this pressure builds up, it slows it down. So you'll know fuel pressure is building as it's going. And now that plunger is slowing down, things are starting to balance out. And then the diaphragm is up here. That's just to kind of help equalize the force. Dampen output pulses is the official purpose of that. So it just dampens kind of vibrating movement. And here, this is from the Piper Cherokee manual. There's different styles of these pulsating pumps. So you're going to be taking these apart for a lab. Make sure you read the manual closely to know what style of pump. Here it is installed in the aircraft. Any questions on pulsating pumps? And I have some to pass around. You can see the coil, the plunger's gone. This sort of has part of the plunger. You can push him up a little bit. You can even see a little magnet and contacts. pump or an engine-driven main pump. So like in any of our S model 172s, if they're fuel injected, if you turn the auxiliary pump on, instead of like a Piper, you turn it on, you hear Cessna, you turn on the boost pump and you hear nice smooth work. Because it's just an electric motor that is turning that auxiliary boost pump to send fuel to your engine. Let's see. Yeah, pretty much all you need to know on that. Questions on that? So then, I'm not sure why they ask you questions on ejector pumps in power plant, because these are only out in the tanks, but they do. So we get to talk about them. Yay! What their purpose is to maintain a fuel supply at the inlet of the boost pump that's in the tank, if there's a boost pump in the tank. So the way the tanks are set up, there are flapper valves between the sections of your tank, so that's letting fuel flow inboard. This is our inboard section of the wing. Fuel flow is flowing in, and these ejector pumps, so here they are, small. This one is taking this one and flipping it kind of over. So then here's our boost pump. Now it's going to be pumping fuel out to our engine, wherever it is. And well, I'll bring it back. There we go. So our boost pump has this, if we're getting too much pressure, this is where the fuel flows back into the tank. But they direct that fuel through this line that goes past these ejector pumps. The ejector pumps are designed that they have a venturi in each of them. So when fuel is flowing through the center of this little ejector pump, it is doing what to pressure? Decreasing, giving us a low pressure, so then that low pressure is sucking fuel from the end of this line into the tank at the inlet of the boost pump. So ejector pumps, there's no mechanical action of it. It's just a venturi that when fuel is sent through them, they are also drawing additional fuel from out here because of the venturi. So what you need to know is they ensure that fuel is always at the inlet side of the pump, and they operate by venturi principle, and their purpose is to assist in the transfer of fuel from the main tank to the boost pump sump. What you're going to see in your written test is a diagram like this. So this diagram is in your textbook. Pretty decent, makes sense. This here, that little point, is what they're trying to use to represent the ejector pumps. So they're trying to show a venturi. Really not a great diagram. Question they're going to ask you is this. What is the purpose of fuel transfer ejectors? And they're going to give you the options to supply fuel under pressure to the engine-driven pump. Yay or nay? Or can an ejector pump pressurize fuel? It got no pump in action, it just got no venturi. Can it transfer fuel from the boost pump sump out to the wing tank? 12. It's not terrible. It's going to start out with asking you ATA chapter for fuel systems, and I'll give you a little heads up. The next question, you're going to go to the Gulfstream 550 manual. So, yes. Thanks, Josh. So, if you look in there, the ATA chapter is going to help you with question number 1. And just, let's see, oh yeah, please read the question carefully, because it says make sure your answer is in 2-digit format only. For example, if it's 15, put 15. Or, because sometimes a chapter will be like a dash, yada, yada, yada. Just put 2 digits of the correct chapter, and it should grade it correctly. And then, question 8, so the first 7 questions are the Gulfstream. Question 8, it takes you to the 414, tells you exactly which manual, the 70 to 85. So you'll be going through that for the rest of the questions. And question 10 is getting more specific. So depending what serial number the aircraft is will depend what your answer is. But we give you which serial number category our 414 is. So make sure you're looking at that serial number to answer the question. And then question 12, we took this diagram from the 414 manual and added in all these cute little labels. So then you'll scroll down and say, label A is whichever component it is. I do want to note that, hopefully everybody's paying attention, make sure your neighbor's paying attention. So here we have a letter J pointing to a component and a letter K pointing to a component. So it's a little tricky because J is labeled near the actual component that's listed in the manual. This component is not going to have a label in the manual. You'll have to use your skills of deciphering from the options that are listed. But K is referring to the component of the fuel system that the pilot in the cockpit operates. Oh. You're welcome. So that should, without exactly giving you the answer, I basically gave you the answer. And if you have questions on that lab as you go through it, let me know. Then lab 2 is engine fuel system nomenclature. So what it is, you have all these components, and on the actual 414 aircraft, the right wing, components A through N, and please note I is skipped, so A through N but no I. You're going to see which labeled component in the aircraft matches these. So you're going to have to be taking off a bunch of inspection panels, and I'll show you some other stuff you're taking off to find those components. One of the components, you will need a mirror and a flashlight to find it, but go to the manual and get a good idea of where the component is according to the manual, and then that will direct you where to look in the aircraft. Then number 3. So there is a part 2 to number 3, which I'll open that up tomorrow. But the main part of probably tomorrow or Monday. So you're very welcome to do questions 1 and 2. If you want to wait on those, that's also okay. But then question 3 is going to the Cherokee manual, as well as question 4, asking about pressure testing the Cherokee pumps. These are pumps that we have, just the pump on the table out here. You're not going to actual Cherokee aircraft, just the pumps on the table by themselves. And when you are assigned, your group will then do question 5. So make sure you do question 3 and 4 first. Pretty easy, just get in the manual, find the information. And that will lead you to what you know for question 5. And I believe Anna is going to be at that station with you. You're going to pick a pump. The pumps are numbered. So down here in this template, write down the number of the pump, because different ones have different problems. And then you are going to disassemble it according to the manual, inspect it, visually inspect it, clean it if needed, reassemble it, and then you're going to do the bench pressure test. So again, nothing on the aircraft, just on the table. Reassemble it, and you're going to do a pressure test with mineral spirits for our situation. And then the manual will tell you how to do a resistance test. So I want you to write down what the pressure was that you actually got, and then what the ohms reading was. And then there is a spot here, did the instructor verify your work and check you off sign off list? So then you'll just put yes, that you were checked off on that. Any questions on those 3 maps? So what, I just started with the schedule. I wasn't sure how the lecture would go today. So this is just the very beginning, because I have all these to add in. But I decided to start with the middle groups, since I've always been starting with beginning groups. So we have 3 pumps, so 3 groups can go at a time. So Zach and Dan and Isaac and Lee and Parker and Josiah, you are the first 3 on our Piper pumps. And if you're super quick, we might get a few more groups. I'll try to grab groups, but we will have time tomorrow, for sure Monday and Tuesday, to be working through those. And then we have time. I'm gonna put 2 groups on the 414, because you're gonna have to take off inspection panels, and then might rain tonight, put them back on. So groups 8 and 9, so Pete, Josh, and Peterson, and then Trevor and Elijah. If you go to the 414 right wing, I'll try to get out there so you're not taking too much off, but focus on the inspection panels on the front of the wing, and then you'll have to take the part of the pod off, but Dean or I will be out there. The rest of you just work on the Moodle portions